The first thing I just want to talk about is our plan going forward. Right now, I'm staying at a spot with limited bandwidth, and I go somewhere else to do these Zoom classes. And with the governor's stay-at-home order, I'm afraid that might not be possible anymore. So I've decided to just go ahead and switch to what we call an asynchronous delivery method. And I'll still be able to hold some Zoom sessions. Like I think, I've been able to attend some meetings on Zoom there, so I just don't know that it's a reliable option to make sure that our classes go smoothly to rely on Zoom. So what I'm going to do is switch to an asynchronous delivery, which just means that I'm going to record videos like for the lecture, for these notes that we go through. I'm just going to record them at home and post a YouTube link. And then you will, watch those videos, take notes sort of on at a time that fits your schedule. And I'll still be available to, I think hold some office hours via Zoom. I think that's still a viable option there. So that's my plan. I will post a schedule this week to let you know when those times will be. And I can also just respond to what some particular needs, or if you are only available at a particular time and you want to set up a meeting to meet one-on-one, I can do that too. All quizzes and tests are going to be take-home. We talked about this already a little bit on Monday. And in fact, tonight we're turning in our first take-home quiz. So we'll all make sure that we get practice, we'll get that experience of using an app or some sort of device to scan our work. And create a submission on Canvas. Has anybody tried using an app yet, or has anybody had trouble finding something that they can use to scan their work? Okay.
I turned in my points back with the PDF scan.
Okay, perfect. And that worked pretty well?
Yeah.
Great. So the tests are going to be take-home. Those will be subject to some rules. They'll be pretty easy. I'm going to post a PDF of the test. You don't have to print it out. If you don't have access to a printer, you can just get some paper and look at the problems and then write out your solutions. They'll be subject to some rules, like, for example, it's not open internet. You shouldn't be using, using Google or Wolfram Alpha to help you do these problems. But you will be able to make a sheet of notes. It won't be timed, but you should just do it in one sitting. I will write out more explicitly what those rules are, and then we could talk if you have any questions about what is and is not allowed. You can let me know, but I think they'll be pretty reasonable rules. And then just like the problem set and the take-home quiz that you're turning in tonight, they'll be, once you finish them, you'll scan, with an app or something, your test and upload it to the submission in Canvas. I'm going to have a test ready. The problem set's already posted. And that problem set's due Wednesday. That's a week from today. And then I just decided to make the test due the following day. So we're doing some work. We're going to be getting ready to finish up the problem set, and then we should be in pretty good shape to work on that test, at least by the following day. I'll post it a few days ahead of the due date, so you could just find a time that works for you between when I post it and when it's due. Again, you should just do it in one sitting, but it won't be available for a whole week or anything, right? So it'll be due on Thursday, so I'll probably have it posted by Tuesday, the 31st. Are there questions so far?
I just wanted to say, I wanted to remind everybody that if you need help on the problem set, I'm also here.
Oh, so, yeah, you should be able to get all the help you need on the problem set. It's also okay. I answered some questions about the quiz. Somebody texted me about those. So, and those take-home quizzes are kind of the same rules as problem sets. It's okay to ask questions. It's okay to get help. I encourage you to ask questions. So this problem set, kind of challenging. It's these application problems. Let's see. Oh, the other thing is I have limited to no cell service where I am. So if you text me, if you have an iPhone and you text me via iMessage, I'll get that because I have Wi-Fi. But if you have an Android and you're texting via SMS, I won't get it until I leave the house and pick up cell service somewhere. So for that reason, if you need to contact me, I strongly encourage to use the messaging feature in Canvas. Email also works, but Canvas makes it easier for me to keep track of messages. Like sometimes, I've been getting like nothing but tons and tons of emails lately with everything that's going on. So like pretty quickly things can kind of get lost in the queue. With Canvas, I just have a little bubble that tells me, oh, I have a message from this class still that hasn't been answered. So that is helpful to me. And if you log into Canvas, you just click on, there's this inbox tab here. And I think that when you click on that, you should be able to create a message and send it to me. So are there questions out there right now about what our plan is going forward? I'm happy to answer them at any time if you have questions later too. Okay. All right. Then we're going to keep going. We're going to do this, get a start on the new chapter. We're going to look at derivatives of trig functions. We're first going to look at the sine and cosine functions, and then the other trig functions. So the functions that we've been focusing on so far are algebraic functions. So they're functions that arise from like the basic, arithmetic operations like adding and subtracting terms, multiplying terms, raising to a power, or taking roots, right? So we have like square root problems, we have fractions with x's, right? The transcendental functions are the functions like that are not algebraic, which just seems like a circular definition, but those functions include like sine and cosine and tangent, right? The trig functions, also the exponential functions and the logarithmic functions. So that's what our focus is going to be on in this chapter. And we start with a couple of formulas. The derivative of sine u is cosine u du dx. The chain rule is ever present, right, in all of these formulas. The derivative of cosine is negative sine. So we're just going to start and get some practice with these formulas. If we want to find the derivative of the function y equals sine of 2x. So first of all, usually, and you'll probably see this in the textbook, they write the function just like this. They don't use parentheses. I like to use parentheses. They only use parentheses usually if there's like addition or subtraction in the argument. I like to always have parentheses, so I make it clear to myself what the u is, right, in this in the function. So this is sine of 2x. The 2x is the argument inside. So dy dx, I'm going to start off, that's cosine of 2x. And then the chain rule says multiply by the derivative of the stuff inside, so multiply by 2. So 2 cosine 2x. So far, so good? Hearing nothing, I'm gonna... It's just so you know, like it's a little hard for me to tell sometimes, most of us don't have our cameras on, and that's okay, but it'll be harder for me to tell, like when you were in the classroom, I could kind of scan and see if somebody was still writing. I can't tell that now if we're not using our cameras, and that's okay if you don't want to use your camera, but I'm just letting you know so that if you need me to stop or slow down, like I just need you to say so. So we'll do another one. This one's a little bit more complicated. Sine 2x times cosine x squared. So there's, again, my argument is the 2x inside the sine, and then that's being multiplied by cosine of x squared. Now, this function involves a sine and a cosine. I know I'm going to have to use those formulas. The overall structure of this function, however, is that I'm multiplying them together. Right? This is a product rule derivative. So I'm going to set myself up, find the product. To execute the product rule. So our f function is sine 2x. F prime, we just found f prime on the other page. Like that was the example we just did, so that's 2 cosine of 2x. And our g function is cosine of x squared. So our g prime, the derivative of cosine, we can look back at the formulas if we need to. The derivative of cosine is negative sine. So negative sine of x squared. And then the chain rule says multiply the derivative of the stuff inside. So that's 2x. So we have minus 2x sine of x squared. Now we're just going to put this together. So dy dx is, let's see, g times f prime, g times f prime, so that'll give us cosine of x squared times 2 cosine 2x plus f times g prime, that's sine 2x times negative 2x sine x squared. I'm going to clean this up a little bit. Putting my coefficients in front, we get 2 cosine x squared cosine 2x minus 2x sine 2x cosine, sine x squared. And I'm pretty sure that's as far as we could go. I guess we could factor out a 2 if you wanted. This is about as simplified as it's going to get, aside from if you want to factor out that 2. Sometimes there's trig identities that we could use, and we're this so close to being able to use the sum and difference formula, except that this factor of x here kind of throws a wrench in that plan. So this is where we're going to stop here. How are we doing so far?
Good.
Good. Any questions out there? Okay, I'm going to start the next one. Let me know if you're still writing or if you need me to go back. This next function, 25 times cosine squared of 120 pi t. Again, I'm going to just emphasize what the argument is. It's the whole 120 pi t that's inside the cosine squared. I'm also going to rewrite this function. I'm going to rewrite it so it makes it more clear to me what I need to do, like what its basic form is. That'll help me figure out how I find the derivative. So cosine squared, right, means that we're taking that cosine of 120 pi t and squaring the whole function. So we've got 25. I'm going to write some brackets here. Cosine 120 pi t. And we're squaring the whole function. We're not squaring the argument. It's the whole cosine function itself. That's important here because the overall structure of this function is that I'm raising stuff to a power, right? It's just that this time the stuff I'm raising to a power is the cosine function. But it's still stuff raised to a power. So this is a power rule derivative. So there's my a function p. That means that dp dt. Let's see, I'm going to bring the 2 down. So I got 50 times cosine of 120 pi t. This would be, I'm gonna write this just to emphasize, but it's not really necessary because it's just to the first power. And so there's the power rule. We'll bring the power down. We have the stuff to the 1 less power. Now we have the chain rule. And look, we're going to see something happen with the chain rule that I'm not sure that we've seen happen before. But the stuff, we have to multiply by the derivative of the stuff inside, right? Which is this cosine 120 pi t. So the derivative of cosine is negative sine 120 pi t. But look, if I'm taking the derivative of cosine 120 pi t, then I have to multiply by the derivative of the stuff inside, which is that 120 pi t. So I have to multiply by 120 pi. So the thing that we're seeing happen here is that this chain rule, now you kind of see why we call it a chain rule. Like there's multiple links to this chain. we have to, it's sort of like this function is like a set of those like nesting Russian dolls. I've got a 120 pi t function stuffed inside a cosine function, stuffed inside the squared function. So that when we roll out the chain rule, I've got a couple of steps to that. At this point, all that's left is to simplify. So let's see, overall I've got a negative 120 times 50 is 6,000. So negative 6,000 pi cosine 120 pi t sine 120 pi t. Now, this is a pretty good form of the derivative. We can actually simplify a bit further. So here's an example where we can use a trig identity to help us simplify. So this is not a formula that you need to memorize, and in fact I'm going to post a sheet like of trig facts. There's some trig facts that you should know, and then there's a bunch of trig facts that you don't need to memorize. I'm going to post a sheet that delineates, like, here's the sheet that you'll have, here's the stuff that you should know. But the double angle formula for sine looks like this. Sine of 2 alpha is 2 sine alpha cosine alpha. So a lot of the time when I am using this formula to simplify, I'm using it in the right to left direction, because what it does is it allows us to take an expression where I have to write it using 2 trig functions, and I can write it using just 1 trig function. That's generally considered more simple. And anytime I have a product where I've got sine times cosine, and the argument inside those 2 functions is the same, then I can use this formula. So I'm going to rewrite them. I'm going to do this in a couple of steps. I'm going to first write this. I'm going to pull out like a factor of 2 from the front. So I'm going to have minus 3,000 pi times 2 sine 120 pi t cosine 120 pi t. And this is what I can use that double angle formula on. That should be just equal to sine of 2 times the argument. So sine of 240 pi t. Are there questions on how we executed, first of all, the derivative part and then the simplifying? All right, cool. Let's do another one. If you want to know, like, we're learning these new formulas, we're working with the trig functions now, so whenever we want to make something a little bit more interesting, we just say, oh, let's try this now with an implicit function. So we want to find dy dx. Here's our equation that sort of implicitly defines a relation between x and y, and we want to find dy dx. The procedure is basically the same. We're going to just differentiate both sides with respect to x. In that process, we'll get an expression that has, or an equation that has dy dx in it somewhere, maybe a couple of times, and then we just use algebra to solve the equation for dy dx. Now, we have looking at this equation, we've got 2 products. Here's a product, I'll call this product 1, and here's a product, I'll call this product 2. So we need to set up our product rule. So our f1 function is x, and its derivative is 1. Our f2 function is, or sorry, g1 function is cosine 2y, and its derivative is, let's see, derivative of cosine is negative sine, so you have minus sine 2y. Now, when we multiply, when we apply the chain rule here, I'm multiplying by the derivative of the stuff inside. The derivative of 2y is 2 dy dx, so we could clean this up a little bit. Negative 2 sine 2y dy dx. Our second product, our f2 function, is sine x. And so its derivative of sine is just cosine. So cosine x, there's no chain rule to worry about there. Our g2 function is cosine y. And so g2 prime, derivative of cosine is negative sine. So negative sine y times dy dx. Okay, I think we have everything we need to put this together. So we're using the product rule a couple of times. Let's see. Just setting myself up. G2 F2 prime plus F2 G2 prime equals, and then on the other side, of course, that's just going to be 0 because that's a constant. Let's see what we got here. G1 F1 prime, so that's cosine 2y times 1. Let's see, F times G prime, so that'll be a let's see, x times negative 2 sine 2y dy dx. There's the first product rule, and the second product rule, gf prime, is cosine y cosine x plus f2 g2 prime is sine x times negative sine y dy dx, and this is equal to 0. I'm going to just clean this up a little bit before I start doing the algebra. So I got cosine 2y minus 2x sine 2y dy dx plus cosine y cosine x minus sine x times sine y dy dx. I'm going to pause there for a few seconds, see if anybody has questions. Okay. All right. All right, so now let's do some algebra. I'm going to, all of my terms are on the left side, so I think I'll just, maybe for convenience, because I like having positive terms, I'm going to throw the dy dx terms on the right side. So I'm going to add the 2x sine 2y dy dx and the sine x sine y dy dx to both sides. So now we've got cosine 2y plus cosine y cosine x equals 2x sine 2y dy dx plus sine x sine y dy dx. All right, I think we all probably have a good idea of what's coming next, right? This procedure is just like when we have always done the implicit differentiation. We've got our dy dx's on one side. Now let's factor it out. And now it's all over but the shouting. We're just going to divide by the stuff in the parentheses, and we get this fraction here. How's that? Hearing an overwhelming positive response. I'm going to assume that things are going pretty well. Again, if you do have any questions as you go through these, just feel free to pause me, stop me. Anybody need me to stop before I move on to the next one? Anybody still writing? Okay. All right, so one more in this section. We're going to find dy dx for y equals tan x. Of course, this is the section on sines and cosines, right? This is we're doing derivatives of the sine and cosine function. So if I want to find the derivative of tan x, I think the first thing I'm going to do is just write it in terms of sine and cosine. Tan x is by definition sine x divided by cosine x. And knowing that, I mean, now I've written in terms of sines and cosines, this is a quotient rule problem. So I'm going to set myself up here for the quotient rule. Our f function is sine x, which means f prime is cosine x. Our g function is cosine x, which means our f function is negative sine x. No chain rule stuff to worry about there because the argument is just x. So dy dx, chain rule, let's see, quotient rule is g f prime minus f g prime all over g squared. So g times f prime, cosine x times cosine x, minus f g prime is sine x times negative sine x, all over g squared. So that's all over cosine x all squared. I'm going to clean this up a little bit. Cosine times cosine is cosine squared. Let's see, this will be a plus. Sine times sine is sine squared. And in the bottom we have cosine squared. Now we are resisting temptation to cancel those cosine squares because of course we cannot cancel over addition. However, there's a nice identity we can use. In order to, like, you might already be familiar, you've all probably taken, like, pre-calculus where you did some trig stuff. I'm just going to remind you, in fact, I could do this looking at my desktop here. So this is the unit circle, right? This is my background on the desktop, and you might have learned trig. We know about right triangle trig, SOHCAHTOA. There's also unit circle trig. They're completely compatible with each other. But for any, I'm going to just draw a unit circle here. I'm going to do I'm going to go off on a little tangent here. Pun intended. So this is a unit circle, which means it's just a circle of radius 1 centered at the origin. All right, so if the radius is 1, we know the coordinates of these points. And if I take an angle, a standard position angle, which means it's measured from the positive x-axis, right? I'm just going to take any old angle, I'll call it theta, and look at the point where it intersects that side, where it intersects the circle. The coordinates are, by definition, the x-coordinate is cosine theta, the y-coordinate is sine theta. And this is a unit circle. So that means that this length here is 1, right, from the center out to the circle. And I drop down a perpendicular. And now I have a right triangle. This length here along the bottom has to be the same as the x-coordinate. This length, this vertical length, has to be the same as the y-coordinate. And using Pythagoras, we find that sine squared theta plus cosine squared theta is equal to 1 squared, or 1. So this is one kind of fundamental trig identity. We call it the Pythagorean identity. No matter what angle you're talking about, sine squared plus cosine squared is always equal to 1. So if we kind of go back to our notes here, that's going to help us simplify. Here we have cosine squared plus sine squared in the numerator. That's equal to 1. So our result is 1 over cosine squared. 1 over cosine squared x. And we have a name for that, right? That's another function. The reciprocal of the cosine function is secant. So 1 over cosine squared x is equal to secant squared x. So there's our result. Now what we just did, we showed that the derivative of tan x is secant squared x. We have by extension basically shown that the derivative with respect to x of tan u is secant squared u du dx. So there's another trig formula. There's another derivative formula for another trig function. And that's what we're going to be headed into in this next chapter. So are there questions before we talk about the other trig functions? Okay. All right. So, on the next page here, we've got these other trig formulas. So right at the beginning here, this first one, this is what we just derived on the last example that we did. The derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. The derivative of secant is secant tan, and the derivative of cosecant is negative cosecant cotan. Now, going forward, you're going to be able to make a sheet of notes on the test, so you could certainly include these formulas on there. But there's, maybe you'll do enough practice that you'll just end up memorizing them, even if you weren't trying to. But there's like a pattern to them. Recall that the derivative of sine is cosine, and the derivative of cosine is negative sine. So comparing the derivatives of the function versus the derivative of its cofunction. You just swap out when I go from one function to the other. I'm swapping out one function for its cofunction and changing the sign from positive to negative. So the derivative of tangent is secant squared. The derivative of cotangent is the negative of cosecant squared. So I'm switching out the function for the cofunction and changing the sign. That same thing happens with the derivative of secant, right, where we get secant tan. Derivative of cosecant is a negative cosecant cotan. Switching out the cofunctions, changing the sign. We'll do some examples. Our first function, y equals 2 tan of 8x. So it's a tangent function. There's nothing, there's no like product or quotient rule to worry about. There's only a little bit of chain rule that we have to deal with here. dy dx is equal to 2 times, derivative tangent is secant squared. Secant squared of 8x, and then multiply by the derivative of the stuff inside. That's 8. So we have 16 secant squared of 8x. I should note that we derived the formula for the derivative of tangent in the last section just by setting up the quotient rule. In the same way, you could find the derivative of cotan. Cotan is cosine over sine. You could find the derivative of secant, which is 1 over cosine, just by using like the power rule and the chain rule, and the same with cosecant. So knowing the derivative of sine and cosine is how we get the derivatives for all these other functions. Okay, so our next example, we want to find the derivative of y equals 3 times secant squared 4x when x is 0.2. One thing we should keep in mind, we're working with trig functions unless stated explicitly otherwise. The arguments inside are always in radians. So just be mindful of the mode that your calculator is in. You might find yourself needing to switch modes now and again. So our function, it's secant squared 4x. So I know that means that I'm taking the secant of 4x function and squaring the whole thing. And in that way, when I write it like this, it makes it more clear to me, more obvious to me that this is a power rule derivative. So dy dx, bring the power down, 6 times secant 4x. That's just to the first, so I'm going to leave that power off. Now the chain rule says I got to multiply by the derivative of the stuff inside, which is secant. So if you look up to the top of the page there, you'll be able to remind yourself the derivative of secant is secant tan. So secant 4x, tan 4x. And again, now we have another link to the chain rule. I have to multiply by the derivative of the stuff inside secant, so multiply by 4. And we get, let's see, 24. Now I still have two factors of secant 4x, so secant squared 4x times tan 4x. There's dy dx as a function of x. And now we wanted to evaluate it when x is 0.2. Four times 0.2 is 0.8. Now I don't have a secant button on my calculator, so I'm going to rewrite this. Secant is the reciprocal of cosine, so I've got 24 tan of 0.8 over cosine squared of 0.8. Okay, so 24, oh, let's see, my mode, I'm in degree mode, so I'm going to change that up. Put into radians. 24 times tangent 0.8 divided by, now I've got to square the cosine function, so I'm going to put this in parentheses. Cosine of 0.8 squared, like that. I don't know if I need that extra set of parentheses, but I'm using them anyway. So 50.91 approximately. Questions on that example? Okay. Let's try another one. T times cosecant cubed of 2t. This is, so we have stuff to a power, right? We could see that there's definitely going to be a power rule involved, but overall, first, before we get to that, I've got a product here. I'm multiplying t by cosecant cubed of 2t. So let's set up our product. The f function is easy. That's just t, and its derivative is just 1. The g function is cosecant cubed of 2t. So cosecant of 2t all cubed, which means g prime is, let's see, that's going to be a power rule derivative, so I got to bring the 3 down. Then I've got cosecant squared of 2t times, the chain rule says multiply by the derivative of the stuff inside the brackets, the stuff that we're raising to a power. So I'm multiplying by the derivative of cosecant, which is negative cosecant 2t cotan 2t. And then times the derivative of the stuff inside cosecant times 2. And we could simplify that a little bit, so we get negative 6 cosecant cubed of 2t cotan 2t. All right, dy dx, power rule. We've got gf prime plus f g prime. So g times f prime is cosecant cubed 2t times 1 plus f times g prime is t times a negative 6 cosecant cubed 2t cotan of 2t. Clean this up a little bit. And I think we could, you know, I would argue that it seems a little bit simpler if we factor out that cosecant cubed, since that is in common to both. So I'm going to do that. Questions on that example? Okay. All right, let's try another. We're finding the derivative of, let's see, tan 2x plus secant 2x all cubed. So this is, I think, right at the get-go, pretty easy to recognize as a power rule. You know, I see the parentheses, I'm raising them to a power. That's a power rule derivative. I'm going to have some trig stuff going on when I apply the chain rule, right? But there's no product rule that we have to worry about here. So let's just sort of see how this rolls out. dy dx. Applying the power rule, I got to bring the 3 down, and then I have this stuff, tan 2x plus secant 2x all squared. So there's our first pass, at the power rule. And then we have to multiply by the derivative of the stuff inside. So look, the derivative, the stuff inside, there's 2 terms that we're adding, so its derivative is going to have a couple terms, which means I have to make sure I'm multiplying by the whole derivative. I need parentheses. And now the derivative of tan 2x, derivative of tangent is secant squared. So secant squared 2x times 2. That's the chain rule at work for the argument inside tan. And then the derivative of secant 2x is secant tan. So secant 2x tan 2x, again, times 2. There's the chain rule at work for the argument inside secant. We could do some simplifying. For starters, I'd say that we can factor out a 2 from that set of parentheses at the end. Also, a factor of secant. Just one factor of secant that they have in common. So let's see, we have 3 tan 2x plus secant 2x squared. And then let's see, 2 secant 2x. What's left inside for that first term is just a secant 2x. And then plus tan 2x. Going to do a couple of things here. The first is just throw this at the front, so I have a coefficient of 6. So I'm going to put that factor of secant at the front. So 6 secant 2x. But then look at what we also have here. I've got a tan plus secant all squared, and then I have a factor of secant plus tan. Those are obviously the same factor, right? The order in which we add those terms does not matter. So we have a tan plus secant all cubed. Questions? Okay. All right. If we're doing okay, then we'll go ahead and start working through our last example. Which is, of course, an implicit differentiation problem. That's how we make things a little bit more interesting. But our approach is the same, right? Like, our basic technique on implicit differentiation is the same. Differentiate both sides with respect to x. In that differentiation process, of course, we're going to have to use these new derivative formulas, but we can deal with that. And then we do algebra to solve for dy dx. We do have a product rule. So again, and I'm going to sort of point out where that is. Maybe you could spot it for yourself right now. I'm going to emphasize what our arguments are. This 2x is the argument inside of cotan. And inside the cosecant function is the product xy. There's the product rule. In this case, we're going to have to use the product rule when we are executing the chain rule for the cosecant function. So I'm just going to maybe set up the work for that. This is a pretty simple one. Our f function is x, which means f prime is 1. Our g function is y, which means g prime is dy dx. So I'm going to just sort of set that aside. And now let's try differentiating. So our first term, cotan 2x, the derivative of cotan is negative cosecant squared. So negative cosecant squared 2x, chain rule says, times 2, minus 3 times, the derivative of cosecant is negative cosecant cotan. So negative cosecant xy, cotan xy. I've got a little bit of mess with my signs here, but I'll clean that up in the next step. So cosecant cotan times the derivative of what's inside. So like that's our product rule here. So multiply by, I'm going to put it in parentheses because I'm going to have to add a couple terms here, times g f prime. So that's y times 1, I'll just write y, plus x dy dx. On the other side, we have y squared, so that's a 2y dy dx. Okay, so as it stands, just to make sure we're pretty clear on this minus 3 cosecant xy, its derivative was right here. Are there questions on how we executed that before we go further? Okay. I'm going to clean up a little bit before I jump into the algebra to solve. So we've got minus 2 cosecant squared 2x plus 3 cosecant xy, cotan xy times y plus x dy dx equals 2y dy dx. Okay, now the next thing we need to do is algebra to solve for dy dx. I've got one of my dy dx's on the right side. That's doing just fine over there. In fact, maybe I'll decide to just put all my dy dx's on the right just for convenience. But look where the other dy dx is. It's inside these parentheses. So I have to get it out, and we're going to get it out the way we usually do, and that is we're going to distribute. So I'm going to take this big factor. I've basically got that one big factor sitting outside of those parentheses. I'm going to distribute to these terms inside. So I got plus 3y cosecant xy cotan xy, and then plus 3x cosecant xy cotan xy dy dx equals 2y dy dx. So all I did was just distribute that factor through those two parentheses. Now what I'm going to do is take this term. I'm going to just subtract this term. I'm going to throw this on the other side. So we got a -2 cosecant squared 2x plus 3y cosecant xy cotan xy equals 2y dy dx minus 3x cosecant cotan dy dx. Whew. Almost done. We're getting close. We know we are because we've got all of our dy dx's on one side, and it's the same like last couple steps. That's always, you know, that as it always works out in these implicit problems, we're going to factor out the dy dx, do some division. So the dy dx times, let's see in the parentheses, 2i minus 3x cosecant cotan. And now it's all over with the shouting. We're going to divide by that stuff in the parentheses, and we find that dy dx is -2 cosecant squared 2x plus 3y cosecant cotan of xy all over 2y minus 3x cosecant xy cotan xy. How's that? Okay. Is anybody still writing? Do you want me to hang out on the screen for a minute? Okay. Well, hearing nothing, I'm going to assume that we're doing okay. I'm going to have these notes posted to Canvas later. The video posted by morning time. As we're going forward, I just want to emphasize or ask folks to check in on Canvas. You check Canvas for announcements. If you have the Canvas app installed on your phone, you should get a notification when I post an announcement. But if you just check this announcements page every once in a while, I'm going to try to keep us updated if there's anything important coming up. You should be reminded of any due dates coming up when you visit Canvas. These are my due dates because it's telling me stuff that I need to grade. But you'll have your due dates on what's due when. And if you have any trouble uploading your submission, if you're having a hard time getting that app to work, just let me know as soon as possible. Again, preferably through messaging with through Canvas, but email will work too if for some reason you can't get to Canvas. Stay safe, stay inside, shelter in place or whatever we're calling it, and reach out with any questions that you have on these problems. You can ask questions about the quiz, ask questions about the exercises. Maybe you've had a chance to get started on the problem set. As you begin working on that, start it right away. Like, there are some problems that are challenging. They're also fun, but that's usually if a problem is fun, that means that we have to work pretty hard at it. So if you get, give yourself time to get stuck and ask for help. I will be in touch with the class with information about when you'll see the next material posted. Again, so we're not going to meet as a class tomorrow. I will have material posted. I'm going to try to have it posted by morning time, but it could be midday. I will send an announcement when it's ready, and then that's how we'll kind of keep this class going. I'll post material. It'll just be posted pretty regularly, but I can send out announcements when new stuff is ready, and then I'll let you all know when I'm doing a Zoom session. I'll have at least a couple Zoom sessions a week, and I can do them upon request, if you want to schedule some time that works for you. All right, I guess I'll call it a day. We'll adjourn for now, and I hope you all keep in touch, and I'll see you in email and Canvas at least.